Welcome. I wanted to walk through the Masters Problem 530, the one that we did in class earlier today. And so again, and show you how this was set up on Excel. So I took the time to actually run through this problem on Excel. And so we have a city of that many people, and the flow rates, 37 cubic feet per second, BOD of the wastewater given, and DO of the wastewater, and all these different things that are with this problem. And so we want to determine, ultimately we want to do our DO sag curve drawing. And so we want to look at a system where we're going to see what that sag curve is and where those minimum values might be. But what I'm going to do in this example is just kind of go through the formulation of all these different data points that would go on this DO as a function of time or distance sag curve. So the very first step is to look at the BOD mix of this wastewater. And so we've got the river that comes in. So essentially the river that comes in, and we've got our pipe that is discharging into here, and we've got concentrations and flow that's coming in for the river and for the wastewater, and then we have the mix. And so what's that mixing zone that is in this location? And so we can use the fundamentals of the mass, the mass balance equation, which I have highlighted right here. And so it's essentially concentration times flow for the river, concentration times flow for the wastewater equals concentration times flow for the mix. And this would be the mix that's down gradient. And so let's see if I can get rid of the pen here. Yep. And so we can look at these cells. So essentially solving for the BOD mix. Looks like we get, so program that index cell up here. And we get about 6.7 milligrams per liter. DO mix, same process. That's another concentration. And then we have our deficit. And I have this D sub naught. And I just have a space here in Excel. That is not to be confused with dissolved oxygen at some particular time. And so here we've got, so this would be the saturation concentration as a function, or minus the D mix that we calculated before. And so with this DO, what's this initial deficit at that particular location? What would that be? And so let's see if we can track these little cells as we go through. So formulas, review. Oh, where's that thing at? Data. Oh, I can't seem to find, so where we can look at our... Okay, I was looking for that trace precedence. So let's look at precedence. And so we're, again, referencing the cells, make sure we put the $ in the equation. Well, not here, but if we're to track that down later. So what we want to do now is to calculate using this, this equation that I have here. This is our Streeter-Phelps equation, and calculate that deficit at some particular time. And so that all gets plugged into here. Remember, this L naught is the mixed concentration. So we're looking at this BOD mix that's right here. And our T, our time, is going to be variable. So we want to essentially set up a table where we've got time coming down here. We've got our deficit coming down, and we've got our DO that's coming down as well. So the crux is this calculation of this D sub x. And so it's a pretty long, laborious calculation. Look at all those parentheses that are on there, but we can see where everything is referenced on here. You could break this up into sections and do this calculation, then this calculation. So look at the reaeration and deoxygenation coefficients. And these, so remember that T is going to be referenced into this cell over here. And then we have our initial deficit. And so let's just track and see where all these things are. So we can go to formulas, trace precedence, and we can see where all the cells are referenced on there as we go through. And so we're highlighting those and make sure that we have our $. So those are fixed as we copy those down. And then we have our dissolved oxygen concentration, which is just our DO sat minus our deficit. And that's what we got. And so I plotted this. And so I'm plotting time. And so I got this up to 10 days. And you can see that our DO sag curves drops down a bit and comes down to about 5.5 or so. Then it comes up and actually goes up above and beyond where we initially were. Remember, we had that initial deficit right in this area. And so we're going to stabilize and come up to about our DO sat, which would be about 8.5. That's what I'm looking for, and this problem is looking for specifics within this data set where that minimum point is, and you can use the formula or find the minimum in your array. And that's essentially how it's done. And so your other homework problems are very similar to this. I'm just looking for a graph with this particular data. Thank you.